Hello, people. All right, so today I'm going to be continuing my stream of hacking CTF challenges. Funny story, um, F4 yesterday asked me if I could keep the how do I go there? Yeah, there we go. If I could keep my recordings, but of course I didn't have that setting enabled, so I missed out there. So what I'm going to be doing now is going to be going somewhere a little bit different, but I will be posting those videos on YouTube, and the goal is to do live hack throughs of approaching CTF challenges. So yesterday we were looking at the pwnable.tw challenge 3x17, and so this was a really cool challenge. I'm actually going to not be continuing this. I'll probably come back to it. So we got a little bit stuck yesterday. I think I have some ideas today, but as I was kind of thinking through this a little bit more, I realized, it may not be a great idea to post live walkthroughs of CTF of these war game style challenges. So these are challenges that are always available, and people can be working through them. So I don't want to spoil any of these things for anybody that's working on them. So I'm gonna probably no longer do these specifically anymore. But what I realized what would be fun is going through old CTF challenges. So specifically, actually, while I was looking this morning for, okay, what are ways maybe that I can get past on this 3x17 challenge, I found this great write-up by a guy in a tuxedo. So shout out guy in a tuxedo. The audio is a bit echoey. Okay. Let me pretend like I know what I'm doing and definitely fix it. Any better? I thought it was working yesterday, but I didn't. I don't know. I guess I didn't test it that much. I can play with levels. Okay, cool. Maybe I did something right. Great. Thank you for letting me know. So what we're going to be doing here, so I found this great write-up of a challenge from a CTF. So Insomni'hack is a great CTF, and this is a challenge that's actually very similar to the challenge we were looking at yesterday. So rather than kind of spoil that challenge for pwnable.kr or pwnable.tw, I thought it'd be great to go back in here and let's go through this. So I will say this is different than I usually do. So I have read this walkthrough. I did it this morning. I've probably forgotten most of it, but so this won't be a pure blind walkthrough here, but that's okay. Let's just go with it and see what happens. So, okay. Let's see, there must be a way. How do I increase my font size? Man, I can never remember. There we go. Control X plus. Okay, so so here's the challenge. So the challenge is called onewrite. If we were playing the CTF, we would have seen this challenge in the pwn category. So this tells us that, hey, we need to pwn the challenge. Right here, we don't have it running remotely yet. So instead, what I'm going to do here is just be exploiting it locally. So well, first, before running it, we always like to run our good friend, the file command, which tells us great information here. So the file command here says that it's an 64-bit ELF, great x86-64. It's dynamically linked, so it's going to be using the system libc. I wonder if that's going to mess up our exploitation. Hopefully not, but that's okay. And then it is not stripped, so that's great. That should give us a little bit more information about this binary. Now we can run it, and it says all you need to pwn nowadays is a leak and a keyword write, they say. I wonder who says that, but I guess we'll be able to prove them right or wrong depending on how this goes. So what do we want to leak? So stack or pi. I like pi. Actually, I don't like pi, but that's okay. That's neither here nor there. Let's say we have an address. Let's write some data there. Okay, so let's see what happens. So it looks like it gave us a memory address. Let's just verify that again by running it. Okay, that gave us a different address. And this does look like something that's on the stack. We can see with the 7FFF, these are kind of standard stack addresses. And the next thing that we'll do is run checksec on our good old, I'm not in work on Pwn. I have a virtual Python virtual environment specifically for this. So checksec onewrite. Okay, so we can see partial row, canary found, NX enabled, and PIE enabled. But of course, with this PIE leak, that leaks out something from there. So we can leak out something from either the stack or PIE, and then we get what will probably be an arbitrary write. So if folks were here yesterday, we remember that this was essentially the exact same interface as the pwnable.tw challenge 3x17. So now let's open up this in IDA, so new instance, and this is the challenge from last time. So let's say we're going to do something new, CTF, so I have old challenges here, and x.py. Cool. Sure, load the debug information. If you got it, always load the debug information. Oh wow, it's pretty large. This seems suspicious. So let's see. I thought when we ran, file on it, it said that it's dynamically linked. Then why is it so large? Let's check it out. So looking at this, just kind of scanning this to look for anything potentially interesting or out of the ordinary. So because it's PIE, so position independent executable, it means that this data, the code and the data can be loaded kind of anywhere. So we see a Fini section, so that's interesting. Okay, we have the init array, the Fini array. We got a lot of stuff in here, string tables. Let's run strings on this just to see where we are. And I suppose I never checked that this binary actually is correct, so, you know. Okay, strings is use, there's some strings. Okay, we actually do get a lot of strings. Yeah, the fact that there's so much stuff in here, oh, well, kind of interesting. We have the compilation string. It says F no stack protector, but checksec said there was a stack protector. Anyways, sometimes your tools lie to you, so okay, we don't want to run this. What we do want to do is look at this. So great, it popped us right into main, so this is nice. And on first glance, we can see that this is pretty easy. We don't really need this this view, but looking at the decompilation, we see, so set vbuff. So usually almost 9 times out of 10 when you see this in a CTF challenge, you can ignore this completely. So the set vbuff is done to basically disable buffering on standard input and standard output. And this is done when you're running a challenge behind xinetd. So this is why the xinetd is how you can run a challenge, have it somebody on the network connect to a port, and xinetd says, okay, when somebody connects on that port, set up the standard input to come from that port, set up the standard output to go out that port, and execute this program. So that's how most CTF challenges actually get run nowadays. So okay, so all you need to pwn nowadays is a leak and a keyword write, they say, and then we call this do leak function. So that seems promising. And on first glance, this sees like everything what we need in here, right? So we have a what do you want to leak, stack, PIE. Interesting thing here is it's pretty clear. I don't think A is ever used. So we could just, if we want to clean this up, we could just say, well, do leak doesn't send anything. And if we go back, we could see that I guess it returns whatever it sent. Okay, so we are calling do leak here. Interesting, stores a pointer on v12. I wonder why it does that, but that's okay. Oh, maybe because it needs, my mic is a bit of a robot. Yeah, increase font size. I don't know how to, let's see. Oh, there we go. I can increase font size. Hey, yo, how about that? A little bit better? So thanks. Okay, you already got to me. Cool. Okay, so great. So yeah, I'll try to keep that in mind. All right, so we want to get so it says, what do we want to leak, stack or PIE? It then prints out just the caret sign. I think when I lean forward, all right, let's try this. How about now? A little bit better? Oh man, now I look weird. The streaming stuff is kind of ridiculous, I'm not gonna lie. It's usually fine when I'm just in a Zoom meeting. A little bit better? I don't want to get too loud, but okay. I feel like I'm hacking at the kids' table, like my hands are up here, but that's okay. All right, thank you. So, okay, so we read, so this gives us the prompt. Read int3 is probably just going to, yeah, so it reads in our input into this buffer. Here, where is this? So we have 15 into a buffer of size 24, reading into there, and then a TOL, so ASCII to long. If we wanted to see that, we could go look at the man page, and the man page tells us that this will return a long, so it's now then translating that. Let's see, how do I see more of this chat? Okay. Yeah. All right. Cool. Okay, so now we have okay, so we're reading here, reading 15 bytes into there. So this is just getting our input. So read int3, int3. We can see that actually kind of a nice feature of IDA is the name of this function must be named to read underscore int3. And so it's actually setting this variable as int3 depending on that. So nice little feature. If it's 1, so let's look back at our output here. So if it's a 1 stack, so it's calling printf, and this will be a, okay, so it says unknown here. So what I'm looking for, what I was surprised by is looking at this, the first argument of printf should be a format string, and this is not showing a format string, and that's because when we look in here, it's probably so small that, and let's actually look, I wonder if the hex view is synced. I think so. Let's synchronize with, yeah, IDA view. Okay, so what we're looking at here is it thinks it's, IDA assumed that this was an offset into the binary, but when we look at this, we can see 25, 70, 0A00. 25 I know is a percent sign, so this is so we need to tell IDA, hey, this is not what you think it is. I think that's U for undefined, and then A for ASCII string, and then that then translates this into a %P, which then should make the pseudocode look better when we look at the disassembly view. Yeah, so now we see %PN. So %P is the printf format to print out a pointer, so that's why we get 0x in hex, so that's great. And then we're printing that out and printing out the address of v11, so v11 is just some entry on the stack, so that's what we're getting leaked. Otherwise, if int3 is equal to 2, get onto v12, so v12 is PIE, so this is the address of the function do leak. So what we're doing here is copying that onto the stack here, the address of the function do leak, and then that's what we're printing out. So that should be exactly what we're printing out, and we can actually verify this really quick. So this is 8A15. So if I run this set PIE, okay, I actually did stack, so let's run it and actually do pi. Yeah, so one important thing when you're looking at PIE, so position independent executables, the last 3 nibbles will be the same. So A15 will be the same, but everything else would not be. Okay, there's double audio. How about now? Does that fix it? Okay, that is weird. I don't know. All right, I will need to, that's bonkers. I guess both of my mic and my Yeti were going in, but Okay, hopefully that is better. Thank you for your patience. Cool. Okay, so back to the nibbles. So a nibble is a half byte. So a byte is 4 bits. A nibble is a byte is 8 bits. A nibble is 4 bits. So that's actually the nice thing about hexadecimal is each digit is a nibble. So A15 here will be this here, and that's what it's leaking out. And because of ASLR, we should see that every time we do this, it is it's a different address. So that's why we're going to have to start with this leak and then deal with things from there. So going into here, okay, so now we basically understood this whole function. So we basically understand everything here. The thing that we may need to know is this V11. We may need to figure out where exactly that is on the stack because we may want to write things that are relative to there. But first, let's do the overwrite. So I guess actually this do overwrite is a bit of a misnomer. We're not actually overwriting any data here. What we're doing is instead of overwriting data, it's giving us an arbitrary read. So let's see here. So printing out address colon space, which is exactly what we see, address colon space. And then now read in int3. So read in a, although int3 is still wrong because it's a 64-bit address. But anyways, so read in a value, call ATOL on it. So ASCII to long. And then we're reading in data. Oh, sorry. No, we're not reading in data here. This is printing out data. And then we're calling read from 0 from standard input into int3 8 bytes. So this is what we can control. So we can control exactly what address we write to. So this is why we can now see this challenge is called onewrite because we only technically get one write from the challenge. So, okay, so we do that and then we return from here. We didn't see any stack canaries. So no stack canaries, no stack checks. So that's great. And yeah, let's see why. Oh, this printf is in here. So yeah, this is definitely statically compiled. I don't know why file says that it's not. Maybe that's something weird. I don't know. You got to go with what you see. You can't just trust random things. So, okay, let's go in here. Okay, so now we basically know. Now the question is, what do we want to do? So we can use this. You can think of it like a scalpel, right? We have a scalpel to change 8 bytes in this program to be whatever we want. That seems like a little bit of a difficult task. Where are we actually going to go? What are we going to do? Like I talked about last time, there is a one gadget tool. Yeah, so part of the problem is we can't just use the one gadget because it doesn't contain this string bin sh. So if we called strings, so one write. So searching for bin. Okay, search for /bin. Yeah, there's nothing in there. So there's no bin, no sh. So there's no possible way that we could jump to a string that points to bin sh. Okay. So now we can't do that. But let's think about where we are. So once we call... so we basically have this hierarchy of we call main calls do leak should if we look at it here in the disassembly, yeah, do leak returns, calls do overwrite, that returns. So one thing we could do is we could use this to, so we can think about what we did yesterday. So what we did yesterday was overwrite the Fini array pointers and redirect something to where we wanted to go. So we could do that. And let's see, the other nice thing here and the big difference is that this code, we could actually jump back to main or we could jump back to do leak. So by changing the Fini array, we could actually do that. Actually sounds pretty good. I wonder if this was done differently, but okay, let's Okay, so the problem is the returning is getting back all the way to Finny. I'm wondering if we could just loop this basically forever. And so if we did our onewrite, so there's a couple ways we could do this. If we did our onewrite and said do leak, when you return, instead of returning back to main, let's change your return address so that you return back to yourself. And that would give us the ability to do another leak. So let's, rather than theorizing, let's try doing that. So here's my Python little exploit. I don't have any remote processes, so this bit me last time, so I'm going to do that. Okay, great. We get the exe, debug, we have libc. Maybe we'll need it, maybe we won't. And the other thing that we know is because this is a huge binary, there should be plenty of ROP gadgets. So I should be able to do ROP. Yeah. So I should be able to use this to generate a chain. But of course, at this point, I only have one write. So I'm kind of getting a little bit ahead of myself. But that should compute. And yeah, definitely can find a suitable amount of ROP chains. So, okay, great. Now we don't necessarily need to do that. But what we can do is take this libc. We are... okay, and let's start interacting with it. So let's run it in GDB, break main, run. Okay, so at least we can see it here. Actually, instead of that, I'm just going to run it. So when I first start, I want to con.receive until. Now, this is something that you kind of pick up the more you do it, is you always want to keep your communication with the remote process in sync. So this is why I put these things like receive until, to where I know that I'm synchronized in what I think the process should be asking for. So here I'm receiving until the caret, and then I can say, okay, con.send line. I can send, let's say, the stack. So if we say that we want to leak out the stack, what I can do here is, so I do that, and then what I'm going to do is output is con.receive until this, and then now this should capture everything from here of standard output from here to, and I think including address, but this should definitely have our leaked string in it. So what we want to do is parse that. So re dot, I think it's search, and we're going to want to search for 0x 0 through 9, A through Z, A through F, and let's say capital A through capital F, just in case there's something weird here. We also want to group these, so we make sure to capture it. Actually, be great. I probably should just define things like this here. So let's see. I'm gonna open up another terminal here. Work on pwn, IPython, import re, help re.search. So I always like to look at the docs of whatever I'm using to make sure I'm doing it correctly. Okay, search pattern string. So here's the pattern. The string is the output. And so this will return a match object. So you have to do, if you're doing this correctly, like you're a, I don't know, programmer or whatever, you would, check to see if you got a match and then select the group. But if I don't get this output, I just want to blow up. So it's actually fine. This is one of the key differences between like writing code for a CTF and writing like real production code. But we can test this real quick if we're not confident. So re.search, and let's do, okay, so output equals like there is some stuff there. So now we could just copy paste this in here. I'm sure there's better ways to do that. Yeah, so now we've extracted that. Is stack address, and I'm gonna call it str, because then I want to get stack address leak equals int stack address string 16. So doing this, I should be able to pop that in there. And of course, because I did not define that, there we go, there we go. Great, so stack address leak, and if we print that back out in hex. Okay, so this printed out the address here of V11. So the other nice things that IDA does is tell you exactly what offset this is. So this should be right at the stack pointer of this, or it's going to be at RBP minus 18 hex. And I just like to verify this because I've seen that Ghidra actually has different numbering here, which can drive you insane when you're trying to write an exploit and Ghidra is showing you different things. But since I don't want to trust anything, I'm going to go here and go back. Okay, yeah, that's where I want to be. Where's my cursor? Move RSP into RAX, RAX into RSI. Okay, so this isn't actually a value, but it is literally whatever's in the stack pointer. And then move that into RSI. Okay, so this is, this address is RSP inside of, this should be do leak. Okay, so we have that here. Now that we've leaked the stack, we can essentially change any instruction, any what's what I'm looking for, any return address on the stack. So let's say, so let's just try to maybe think about, like, let's say we wanted to do a leak again, so we could jump back to here. That way we could leak out the stack. We can leak out PIE and start kind of going from there. So we have this. We've leaked that out, and then now we go back here. So now it's going to ask us for the write. So what address do we want to write to? So con.receive until. Oh, we already did that up here. So important thing again, this is how I know where we'll actually be. So okay, receive until there. So it's awaiting our address. And now we have to figure out where it is that we want to write to. So what I'm going to do is run this in GDB, so run the challenge. I'm going to, let's just run it. I'm going to leak out that address of the stack. So, and again, so this is, because this is running in ASLR, because it's running in GDB, ASLR is disabled. That's why the stack looks very the same, like 7FFFFFC. That's kind of like a classic stack looking pointer. And I'm gonna do Control C, then go up the stack up the call stack here. This was in readint, do overwrite, do leak. So, okay, so now I'm in do leak. I want to examine 20 giant from $RBP. So I want to examine from the base pointer where we are in do leak. Why does it say libc csu init? But for now, I guess let's ignore that. And do leak main. The base pointer. Why is the base pointer like this? RSP. Yeah, that's weird. Okay. Let's go down into do leak and $RSP info. So I want to look at the registers and I want to see, why is the base pointer pointing to a weird, why is it pointing to libc csu init? Because it doesn't use the base pointer. Okay, so we can see this function here subtracts 18 from RSP, And then it's calculating each of the offsets according to RSP. So it's actually not even using the base pointer. Okay, wow, that's interesting. So I wonder if this number here of RBP minus 18 is like a hypothetical of if there was a base pointer stored, that's where it was. So the stack will be different of this function frame of other stack frames that we're used to looking at, because we don't really see, because there's no base pointer. And we can actually verify that again at the end, because rather than a leave return, it's just adding 18 to RSP and then returning. So now that we know that, and we know the size of do leak, where are we right now? Inside do leak. So X, 20 giant X, $RSP. This is pointing out junk. So this is where the stack pointer currently points. But it should be the case that subtracting 18 should be where RSP was. So then these should be all the values on the stack. And then if we look at what value was, oh, did we capture that output? Yeah, here. So this is, and I'm going to go copy this into my scratch register. Control X. There we go. So this is the memory address that was leaked, because what we're trying to do is figure out where exactly that is. So that's C390, so C39, so this is 98, so that should point to right there. Great. And so I'll do minus, just want to look at more of this stack, and I kind of want to know, okay, where are the instruction pointers? I guess XI $, RIP of where we are. Okay. So now we can see a little bit more from here of the function pointers. So now 7 FFFF7, this is do leak. So, and if we look up VM map, that could have also answered my question of seeing which ones of these are executable. So we can see that the code is being launched into essentially 7 FFFF7, which gives us a nice thing. So these are all function pointers. It should be maybe return address pointers onto the stack. It was tripping me up that this and this kind of look the same. I mean, I know now that we kind of dug into it, it doesn't, but hey, live and learn. Okay. So now, what's at RSP minus 18? So that's at the top of the stack. So if we look at the epilogue of this function, the last thing that it's going to do is add 18 hex to the stack pointer and then return. So this should be the return instruction pointer of where we want to go. So XI, so that will be and that will be push. Wait, what? Why is that there? That. So we're in do leak, so it should be main. All right, we're gonna step through this. Okay, it's asking for our input. Let's get out of that, finish that, do overwrite. So data, do leak is where we want to be. Yeah, we want to be do leak. So, okay, so we just called the overwrite. We did the overwrite, and now we do that. We add 18 to, we're added 18 to RSP. What was I doing? Subtracting 18. So that got us to the root of our problem. Great. So now we can see the RSP is currently pointing here, C3A8 and X5I. Yeah, so that is the epilogue of main. This is where we're going to jump to here. So what we'd really like to do now we have to look at, we can change any of these values. So again, like I said, we can overwrite the last byte here, but we can't overwrite any other nibble because those will, because we've leaked out a stack address. So we know the locations of all of these return address pointers on the stack, but we don't know these values. So the only things we can reliably control are the last byte. We could also control 2 bytes. Remember, we can't write half a nibble. We could try to write 2 bytes, but then we'll only succeed. Well, I don't know if it's half the time, but we'll have to, no, that doesn't make sense, but we'll have to run it many times until we get that last, that nibble correct. So that'd be 1 out of 16 times, let's say. But let's not try to do that. Let's try to overwrite here. So we could basically, now, what I like to do, let's go here. So this is an address in main. So the question now is, can we just like jump back to somewhere else? So we want to be in this view, and we want to be specifically in this view because this is going to I can't remember. There's linear, I guess this is linear disassembly view. So what we're looking for is B09, and that should be the end of main. So here's main. B09 is where we're jumping to here. So what we could do is jump to anything that's B, like we can't jump to this AFF. We could jump to B00. Why is there no B00 here? Because this call to puts has that in there. So we could jump to, and we'll just look at these instructions because we're not really looking at ROP. So we could jump to, when it returns, we could actually jump back to this 04 to call do leaks again. And that actually sounds pretty good. I think that may just be what we want to do. We can see quickly if there's anything else here. So we could jump all the way down. We said B. Yeah, so B and then this byte. So we have a decent amount. We could jump all the way down to, let's see, B, C. So we could jump anywhere in here, any of these instructions. We could divert control flow here. We can now do the same analysis of the end of dual leak. So because we know where that is, we could say, okay, this call do overwrite. So do overwrite's return address will point to here, AB20. So we could actually go to anywhere here. We could go all the way back up to the start of do leak. We could even jump into partway into do overwrite. So we have a lot of opportunities here actually with these return addresses. So this is pretty cool. But let's just for right now do what we want to do is let's just jump back right before this call to do leak. So what we want is for, and I got this from here. So we are currently in do leak, and we want basically do leak when it returns, it will, so this ret is going to go from here all the way back to B04 right before this to call back. So then we should jump back to ourselves. The stack will likely change, so we'll need to deal with that, but maybe not. Let's see. Maybe that will get us like a nice infinite loop. I don't know. Okay, so so now this is where we need to do math. So this is the address that we've leaked out. The value that we want to change is here at 3A8. And man, I always hate doing stupid hex math, especially with subtraction. So 24. So that means if I leak out this plus 24 and cast it as hex, that will be C3A8. Great. Okay, which is the value that I want. Okay, so, and basically I need to, anytime I'm doing anything on the stack, I want to do it relative to this leaked address. So that's the stack leak address. Now I want to mess with do leak saved RIP. Saved, yeah, let's just call it do leak, no, saved RIP is going to be stack leak address plus 24. And because I'm doing just a relative offset here, then it doesn't matter what this address originally was, as long as I can leak it out, then I'm good there. So do leak saved RIP. And then, okay, so now it's asking me for the address. So that was a hex to ASCII. So so what I need to do is then con dot send line do leak RIP. That will translate it. So it's currently an integer. It'll translate it into a string. And just because I'm being nice, I can encode that as bytes. So that will turn that into bytes to send out. And that will send out that with that. And then we should, running the challenge, address, and then data. So these is when we send the 8 bytes. Now, let's go to do leak. So do leak here, hello. Do overwrite is what we want. So this is reading in 8 bytes. Now, the nice thing about the read system call is it will only read what's actually, it'll only read stuff that is there. So it's not going to pause and what we call block. So it's not going to block waiting for us to send 8 bytes. It's going to do whatever it has. I need the F for the F string. Thank you. You know what? It would be really nice if y'all would just like, and I should have noticed because it didn't highlight here, or it didn't change it here, but thank you for that. So the read, reading in 8 bytes, it's up to 8 bytes. So it will read at most 8 bytes. And this is why the read system call returns an integer, which is the number of bytes that it's read. I think it will block until it has at least 1 byte available, and we can quickly verify that. But I'm man to read. Read attempts to read, blah, on files that support seeking. If count is 0 in the absence. If count, return value on success, the number of bytes read is returned. 0 indicates end of file. So this is how we tell we've reached the end of the input, is if 0 is the end of file. The file position advance. It's not an error if this number is smaller than the number of bytes requested. This may happen because fewer bytes were actually available, because read was interrupted by a signal. Anything could happen, right? So as long as we get any bytes back, then we're good. And we know it's not going to return 0 because it can't tell 0. 0 means there's never anything more to read from here. Okay. All this to say, what we can do here, and now we need to be very, very careful. So this is when attention to detail will save you a lot of debugging efforts. The question is, will the do leak function prolog be fine with the overwrite? I think so. Let's try. So if you accidentally do this, so what do we want to change? So we want to change the least significant byte. So I think I'm pointing there. This will be something I will debug because I honestly don't remember Indianness. So I only want to change 1 byte. I want to change the least significant byte to be right in mains. This is the wrong program. Close that out so I don't make that mistake again. That's always embarrassing. Yeah, we want to go right here. So we want to change it to be 04. So what we're going to do is send 0x04. So send, and this is where you'll get into trouble. So, and I'm not going to step into this to show you this, but maybe you've experienced this on your own where you are sending input and you accidentally use send line. The question is, what will happen here? It's going to send 04 and then it's going to send OA, which is a new line. And the read command will read in 2 bytes and we'll place that there, which is not what we want. We only want to change 1 byte. So we need to be very careful when we're doing these kind of things to only send just that 1 byte. And again, even though it asked for 8, it's still going to do this happily just fine. And so if we did this all correct, we should loop back up, see it'll actually ask for us to leak again. So now we can say that we want to leak the PIE. But right now, I think we've done enough here that I don't want to go too far without actually checking this. So this I don't need, and we'll just go interactive from here. Now I do want to debug this. So, well, I guess we can YOLO it this first time. Okay, running this. Okay. It crashed. Cool. So let's debug it and see why it crashed. Okay, so running it here, continue. What's going on here? Okay, that's frustrating. It's not working correctly. Huh. Okay, I'm specifying it. Oh man, this one. Okay. Yeah, just weird that it didn't crash in a segfault or something, but maybe it's actually exiting. So, okay, at least now we're breaking on main. And so we want to break on do leak. Actually, we want to break on do overwrite. This will just break in everywhere. So continue. We're in do leak. Now we're in overwrite. So subtract 18 from there. Call the printf. So telling us the address. And then now I think I see the problem. So we can actually see, and this is what's nice thing about debugging, is I messed up the input output. So it received this address. I then sent these bytes, but then I also sent 1 byte of 4. But the problem is it may have read all of this in one go. I'm actually not sure. So what I'm going to do here is make sure, because I did not make sure to wait until it's asking me. So before I send this, receive until what is it? Data colon. I think it's space colon. The other thing is, if you don't get it directly, you will have bad times. So I think it's exactly like this. So I almost always copy paste this just so I don't make any mistakes. I like removing as many possible places for mistakes to happen as possible. So let's do that. Break do overwrite. Continue. Okay. So now we can see a difference here in our debug output. So we sent the address, but now we're waiting until we get the data and then going to do that. So let's go here. We're going to call printf. Yeah, so it's asking for the address now. And it's not doing anything. Oh joy. Okay, so somehow you got desynced. So receive until the address. And then I put this in the wrong place. Eventually we'll probably make functions to make this easier. But so I had these swapped, so I was waiting for data instead of sending the place that I wanted to do that from. So break do overwrite, continue. Okay, so printing out address, and then it sent this back. So then it's going to call printf for data. So this is when it's going to then read in our data. And now we can see that we sent 1 byte of 4. So we should see, so this is cool. So now we're at the read syscall. So one thing, we can copy that value because that is going to be where, oh, this is great. This is our main. So we can actually see that this was the address that was leaked. So that we properly did that, because how do I know that? Because that points to this main nop. So this is the return address. So if everything is correct and we want to copy this, so after we execute this read, we're going to check 2 things. A, did we read 1 byte? And B, did we change this least significant byte here to be 04? So we'll step over the read system call, px rax, to look at the rax register. That returned 2, which is not great. Why did that return 2? Well, let's check that address. So x1gx, x1gx. Shoot, I messed that up, but that's okay. There we go. That's the buffer. And okay, so we see we did 04 OA. So this must not be red. Yeah, because that's the least significant byte here. So I need to change this. I'm getting bit by things that I told everyone to watch out for, but sending that should return that, and then that should work. So we can do this, break, do over, continue, stepping through, getting the address, printing out data, calling the read system call. Again, it's a different address here, and then x1gx. Now this is 04, so now if we x5i that address, yes, we get this call to do leak. So now when we return, we'll go back to, will we? Where are we? Do overwrite will go back to do leak because we changed the pointer of do leak. That makes sense. Okay. Yeah, so we will go back to do leak, and this should be, yeah, now we can see that in Jeff that we are going back into the call to do leak. So we do that, and I think this creates an infinite loop, which is cool. It's great. So now we're getting the what do you want to leak? So now we can say, well, since we already had our stack leak me out, some pi, and that's going to ask me for an address. Sorry, I lost the thread here. Okay, so it did exit, so we don't get like an infinite, it does not create an infinite loop. I bet it's because the stack, oh yeah, because we don't call that function. I bet we could fix that and with some gadgets or something, but cool. So, okay. We just did that. So now, right. Okay. So now we can leak again. So we already got the, so now we want to receive input until there. Send line B2, so this, I'm gonna put a little comment, PIE, and this is stack. So send that, and then we'll get the address again, but this is not a stack address, this is the address of, what do we call it, do leak, I think. And that address of do leak str and 16. Great, now we have this, and now base. So I think, all right, let's try this. I know of a way to do this. I think you can set the base, Pwn tools elf set base. If anybody knows, please drop it into the chat. Base, I think you can set the base address and then get values from here. The other thing to do would be, let's see, I thought I saw this. Let's see, and this just helps changing the base address. There we go. It's in Pwn tutorials. So there we go. It's right here. Changing the base address. Maybe you can't read that, but that's okay. Address. E.address. Cool. So that tells you where that is. So nice. Okay, this is great. So, oops, no, I definitely don't want that. What I do want, now that we have that, I can say that, well, this is loaded at where? Exe, and I'm also not great. Symbols. Exe, symbols. And this is part of why I'm doing this, is because I want to learn this stuff. So what we just got was do leak. So if that was the address of do leak. Then if we subtract that from there, that should give us the base of this. And so now if we get like exe.symbols, and let's, okay, I want to try that so I can show debugging this. Let's not debug the whole thing. I'm pretty confident this will work. Let's do this. And of course I don't have that. Pip install ipdb. Sweet. Okay, so now I'm here debugging. So now I should have, let's, so this is what we leaked out as the address of do leak. And now if we print out exe.address. So now we think that the binary is loaded here. So now if we say what's exe.symbols of main. So the nice thing is because basically Pwn tools, because it's parsing this elf file, already knows all the different offsets. So once you tell it where this address is located, then we can know all of this. So we can do leak, we can do overwrite, and we can use those from here on out, and now we're good. So this is excellent. This is exactly what we want with this leak. Okay, but now we have another write, and now what we need to do is debug this and figure out, okay, what is the problem here? What's going to happen? So where are we going to jump to afterwards here? So let's debug this. How are we doing on time? Okay, 3:30, making great progress. So break. Let's see, do overwrite, continue. Okay, we already know this works. And now we've leaked everything. So, okay, this is our second overwrite. So we're just gonna say don't overwrite anything here. So I'm gonna say 0. And next instruction. Actually, I'm going to say fin. So fin is a great thing that ends the current function. And so it's asking for data. So let's write 0 to 0. Okay, so now I'm at the end of do leak. So I just called do overwrite. And let's look at the stack. $RSP x.10gx, $RSP plus 0x18. So this is where we're going to go next. Which is back in main. So yeah, so that was that value that we changed. Now the cool thing is, so because we leaked out the PIE, now we can actually redirect this kind of, I mean, not even kind of, wherever we want. So we could go anywhere in the program. So we basically widened our control of this program from being able to redirect a saved instruction pointer on the stack from basically one byte's worth to anywhere in this program now. Okay, so pop, that goes there. And now this, I think, is where things break. So if we look here, x5i, no, I said plus 18, not plus 18 because we're right there. So x5i here. So I'm surprised this doesn't just like exit. I mean, I guess it should. Oh, it did just exit. Okay, cool. So now what we've done here is been able to get the program to execute twice. So being able to leak everything twice. So what we'd really like to do is, yeah, I'm trying to think. So we can execute this once, do it twice. I know how the walkthrough was able to do it. So they basically went to the Fini array and overwrote some stuff there to change those bytes. But what I would like is be able to do as many reads and writes as possible. So, or not reads, but writes. So now we've basically, from an ASLR perspective, we've broken everything about this binary that we want to break. We know the address of the stack. We know the address of the binary, the PIE, which also gives us all the other information about the other segments. So .data, all that stuff we know, and now we can use that ROP chain. The question is, of course, getting that information inside there. So so let's look at our ROP chain. So, we have a significant amount here that we need to get in. So what I would... Okay, so if we think about this, what happens is I do one write. That gives me another write. Yeah, so the question is leveraging this in order to... Because what I would love to do, and where was the start of do leak? So we jumped. Yeah, do leak is here. So we jumped. Right. So we changed do leak to jump not after that, but back to that call. And so right. So we did that ret. Yeah, so by jumping into do leak, in the call to do leak, what would be great, I think, is if we're able to jump back to the start of do leak. Yeah, then this way, this should get us, I think, infinite reads and writes, but let me think about... So let's see if we have the nope. Let's see, do overwrite. So it's return. Honestly, so the beautiful thing is if you could just call this do overwrite function over and over and over and over again, then you've essentially won, because you can just write your ROP chain anywhere, and then your last couple things, then write a then use a couple gadgets or something to get to where you need to go. But you could, use this like this to just, you could actually even write it onto the stack, and then the very last thing you do is change that return address to the start. Actually, I guess if you wrote it backwards, that would work. But I guess the question is dealing with the stack, so or dealing with the stack misalignment, because you want, so we ret there, which should have popped. I think what I'm gonna do is need to, how do I draw in here? Drawing always helps me think through these things, but I don't know. Okay, I'm gonna hide my screen for a second. Let's see. Hey, that worked. Okay. Let's see, notes. Okay. All right, yeah, here we go. I use this stuff for class, but that's okay. Let's, new note it is. Show my desktop again. There we go. Increase the font size as requested. Cool. And, okay. So what we're essentially overriding was so we were overriding the saved instruction pointer of do leak. So this was, oh wow, that's a huge, how do I, yeah. So, okay. Sorry, I'm not the best artist, but that's okay. Okay, so my stacks grow down. So what we have here is saved RIP of do leak. So I'm just gonna call this DL here, and then so emulating kind of this last thing here, we add 18 to change the stack pointer to here. We do a ret, which is essentially a pop RIP, so that changes the stack pointer here, and then this is now where we're executing. Right. So this call, so now we do call do leak, which then overwrites this saved instruction pointer, which pushes a new instruction pointer onto the stack and starts executing. So even if, let's say, I was able to do something here in do leak, that doesn't really help me, because once the program is done executing, it'll go and start executing from whatever's here. Now, so that's with my second. So with my second write, let's see. Okay, so if I was able to jump back to the start of do leak, which the second time I could do, because I know the stack, so I know exactly this location, and I know exactly, so yeah, okay, so this is great. So first time through, we leaked stack pointer. Second time through, we leaked PIE. And now it doesn't really matter where we jumped the first time. So that was our first time. Now the second time, because now we can redirect this wherever we want. So now we call do leak, and then now with this return n, we can change, and it's actually that exact same value, so we don't have to recompute this, because the stack should be consistent, but we may have to debug that. So when we do that, then we'll know where to go. Okay, so then where do we want to go next time? So let's see, because what do I really want to do? What I really want to do is get multiple of these writing. So if I could jump anywhere after this. So again, same thing will happen. So we'll push a new return value. Well, I guess maybe it won't be at the exact same place, but let's say we get this call. Yeah, so the call goes here, pops call, pushes it there, and then decreases 16. We get another read write. And then now we've changed this anywhere. So where do we want to go? We could go to let's see. I don't want to cheat and look at the thing, but I may do that. I need to go in 20 minutes. But so we've read everything. Now, if we could get here, what we really want is like a push. What we'd want is a gadget to just continually call this do overwrite. So what I want here is to jump. Now here's the read call. Although read is a system call here. 0. So the address to jump to is here. Yeah, so if I can control RDX, I can overwrite arbitrary things here, because I could control this return value here to jump, let's say, back here, which would then, oh, maybe that's pretty good. So let's see. Yeah, but the problem in there is our EDX will be the same thing there. My thought is if I jump back here, RSI, well, if I jump back here, RSI should be whatever it was in here, which means my buffer pointed to on the stack, so I could do this again. Okay. So, feel free, I'm going to cheat in a little bit, but let me know in the chat if you have any thoughts here of where I want to go. So what I want to do is let's see, and even if I jump to right before the call to do overwrite, that'll push that on there again. And the other problem is because I popped, let's see. Because I popped this value off the stack when I'm here, now when I redirect, whatever I execute will pop up on above it, and that's the whole basis of ROP. But what I really want to do is, I want like a jump. I want to like jump there. Okay. Well, that's okay. This is why we learn. This is what getting stuck does. I'm going to quickly info leaks, partial overwrite. It's the B9. Yep, we did all this. Great. Partial overwrite. Okay, great. So overwrite the least significant byte of the turn address to be 04 instead of 09. Hey, this is exactly what we did. Okay, so we're able to call do-leak again. How it takes our dword write each time we do so. So past the initial info leaks, it doesn't serve much of a purpose to that. We write a hook to the their turn address to be this way. It will call the call do-leak instruction. So when it returns, it will call do-leak again. Yeah, okay, we did that. Great. So now we're able to call do-leak again. However, it takes our dword write each time we do so. Past the initial info leaks, it doesn't serve. We will write a hook to the Finalizing table that contains a list of functions. That way we can have the oh geez, that's smart. Okay. Also, since after a function is ran, it moves on to the next entry. We need to write at least 2 entries for do-write address. See that it is okay. So so it's basically saying like, okay, now that we can do this, we can actually exit, which is what we just did, which gets into the Finny array, and then go back to do overwrite. So the problem is, okay, so we got that. They'll give us two separate, we have 2 entries in the Finny array. They give us 2 separate dword writes. Use the first one to write the address of what? Each time we call, the return address will shift the address they use for by the stack up by 8. We can find the return address. Okay. I guess I should have studied this more, but I tried to not do it as much. But okay, let's go with what we got here with that little nice hint. So read elf. So the Finny array is here, and we can look at that here in IDA. Okay, do global detours aux Finny array entry. So the init array. So this is where it's at, 2ADF, and I think, oh, I see, that is the exact name of this. So I think that symbol should get us that in there. So I guess I can actually import pwn exe.symbols. Nope, that is not a symbol. View it in hex. Okay, 2ADFB0, great. And okay, 2ADFB0. Okay, so that'll get us the address there. So let's see. So now the yeah, okay, so now that we got that, so we've leaked out that address. Now it's going to ask us, oh, it's already asked us for the address. So let's con.write and is equal to, oh, pop that in there. Okay, so that's where the array is. So the address we want to write to is this array, dot encode, and it's not right. I mean, I think that will work, but we actually want to send, and then con dot read receive until. And now the fact that I'm copying this is probably bad and should be a sign that I should make this a function. Now I don't just want to send 4. What I want to do is send us back to, and let's see, I want to send us back do, overwrite. Exe symbols. Send p64 do overwrite. Okay, great. So this should actually then, we should be called on the Fini array. So don't forget after string again. Oh, gosh, how did I do that? Amazing. This is basically pair programming. It's perfect. Okay. And let's run this and see where this gets us. Okay, so what I'm going to do is run our exploit. And I want to set a breakpoint. We should hit this do overwrite 3 times. So continue. So the first time, the second time, and p64 is not defined. And this is the one function that I like having named in. I should just update that in my script. From pwn import p64 p32 and probably unp. I can't remember, u64 u32. Okay, 1 2 3. Cool. Okay, so this is amazing. So now we can see that from start, so we called start, libc start main, now we're calling exit, run exit handlers, libc csu fini, and now do overwrite. So now it's doing, we're getting one more write. And so let's go up. Actually, what I want to do is view this in the old trusty in here. Okay. Go up x5i. And this is actually exactly what we were looking at before. Let's also set a breakpoint here. I want to, oh, it's not going to work, but that's okay. So now we'll get another overwrite here and into, let's say, 10. And what I want to do is to make sure we still get control. Okay, so now we're back here. P/x rbx. What's in rbx is 0. Okay, so this is the last element of the array. Now the important thing we need to figure out is how many elements are there here. So we can actually easily do this by setting a breakpoint here. So now we're going to just quit out, redo the exploit, and continue. Great. Okay, so now we're here. So the address in the Fini array gets executed before exit. So yes, these are the cleanup functions. So all the addresses there should be executed. Now the question we're trying to answer now is how many of them. So it should be in this, I think either RAX or, yeah, the V1 here is what we want. So that this line, this load effective address, is what we're looking for. Yeah, this is really cool. I mean, this is how like the loader works, because it has to do a bunch of work before the program ever starts, and this is how it has to clean up and do other things. So that's why this functionality exists. Okay, doing stuff. There you go. We go load effective address RAX-1 into RBX, new line x p/x $RBX 1. Okay. This is hilarious. Okay, so now we've hit a point where I think we're screwed. And the reason is, yeah. So this Fini array, unless this is a different version. Huh. I mean, it's possible. So the problem is, or the difference is that this says that there's 2 Fini array entries, but this says there's only 1. This is actually also confirmed in IDA. So if we go to that, oh, what was that? What do we call that? this. Yeah, so this is actually what I was afraid of, is that the end is here, the start is here, so there's only 8 bytes in the Fini array, so we actually only have one thing to do. Because I think the idea in the original one is, since you have 2 entries, you overwrite the first one, and then that overwrite, you overwrite the next one to basically go back to the start of this function. And so then you're just constantly iterating over these 2, and that's how you get your infinite read-write. Now maybe this is from a different one. So this says Insomni'hack 2018, and this says Insomni'hack 2019. But I think these should be the same. So I'm going to quickly look up CTF time hack 2019. I wish somebody had a MD5. Insomni'hack, I think they called it a teaser. CTF events. Let's see, an Insomni'hack event. They have the teaser 2019. Events and write-ups. onewrite. Cool. Okay. Okay, override PAE with main, program ends, and exit will be called. It calls this. So this function call. So again, we jump to main, leak stack address, write a RUP chain in the BSS. Ah, shoot. Well, okay, just spoiled it, but got it. Okay. Oh, hey, Mahalo. Nice to see you there. Yeah, doing from Insomni'hack 2019. I had read a walkthrough. I think it's from a different version or something, because the approach they took is different. But essentially, so I was right. So you can create basically an infinite loop here. So what we're going to do here is specify this entry rather than go back to do overwrite, which just does that and returns. What we're going to do is main, but that kind of doesn't make sense. Leak stack address. Yeah, I got all that. So again, we jump to main. This is because we have like infinite loop here. Let's see, Korean write-up. It'd be fun to see if we can figure it out from there. Okay, the function ends. So blah, blah, blah. We go back here. Okay. So write a RUP chain to the accept. So I need to write 8 bytes somewhere and jump free from the main function again. You can adjust the stack by omitting the function's prolog or epilogue appropriately. Manipulate the return address. Oh. All right, let's see if what jumping to main gets us. I think we may have the same problem where we went all the way back and then go all the way here, but let's at least see that. So now we have this break on main. Continue. Our first time on main, our second time on main. And so, yeah, great. This is so awesome when it just works by changing this thing. Oh, gosh. Okay, so now we'll go through again, but the question is x.20i $RIP. So what I want to see is, yeah, there we go, the ret. I want to break here and basically think what's going to happen. I think because we're not going to go back to start. I wonder if I could go all the way back to the entry point. Would that get me? Huh. That'd be interesting. But let's see at least where this gets us. So what do I want to leak? I don't really care because I've already leaked out both of these values. Right to 0, 0. Yeah, so now we get back here. Okay, yeah. Okay, yes, exited. That's what I thought. What if, let's try something crazy. What if we actually went back to start? That would actually, the idea is this would call main and then it would call the Fini processor or whatever that is again. Let's see. Does it actually know the continue. Yeah, okay, great. That definitely doesn't work. Okay. Why would I want to go with a 3.0 write-up? I guess I should stack address, jump again. I'm going to get into the stack pivoting and okay. Jump into the main function again. Yeah, get an infinite loop with a stack pivoting and write a RUP chain. How? Huh. I guess something's just not working in my brain about this one, but let's see. Okay, jump again to main, find a way to get infinite loop and write a RUP chain in the memory. Yes, that's what I want to do. Because actually we were able to write just 8 bytes every time. We could use this to return to the main function. So we just need to look for an existing gadget in the memory so we can write 8 bytes somewhere and jump again to the main function for free. Ah, okay. It just had to put a gadget that does pop at stack plus 50 and to put the address. Wow, okay. Interesting. Okay, so yeah, this was the key, is trying to get some kind of loop. I guess I was trying to do it too easy or something, but we don't really need that. We got it without that, so that's good. Put the address on there. Oh no, I got to go in 3 minutes. Oh, I really wanted to finish this one. Okay. While true, do exploit. That's funny. One leak, one write, any possibilities? Yeah, there is a lot of different ways to do this one. Okay. Cool. All right, well, this is to always, okay, so hook function inside, the exit function we call this remain returns us. If we change one of the functions into start, fortunately, no. Yeah, okay. Hey, this is exactly what we just saw. Well, if we cannot return to start, why not hook FinArray into functions like, actually this turns out to be the correct, but not necessarily intended method. Or the exit function will not be called as a subroutine return, so we cannot restart directly. Luckily, see, this is the problem. The binary that we have, there are not 2 entries. Otherwise, we could do this. So I think we have to figure out the other ways. So I think it's... yeah, so we have to change 2 entries, use the first one to overwrite return address. Okay, anyways. All right, well, thanks everyone. Man, I really wish we would have got this one, but we will. And yeah, I bet this exploit doesn't work against the version that I have. Yeah, I will try to do this again. So thanks everyone. Bye.